Quick review, very brief, of what we've already seen about motion in one dimension, and then give you a preview of what we're going to do in Unit 1B, where we're talking about a new concept. We've discussed it a little bit, but we're going to focus on that fifth concept. The four concepts that we saw in Unit 1A were displacement, velocity, acceleration, and the kinematic equations, and we applied them in free fall. But going back just for a moment, there is something obviously more basic than displacement, and that's position. So that's kind of our zeroth concept. That just means where you are in one dimension, because we're talking about one-dimensional motion. So you might be at a given place on a number line, in the x direction, or in the y direction, or even in the z direction coming towards you. Okay? But then we saw the displacement is change of position. So if you change from one initial position to a final position, that's displacement. Then when you measure the change of position over time, for instance, how a car moves from one location to another in one direction, either forward or backward, over a period of time, that is its average velocity. The change of position over a change of time. Then, what is acceleration? It's the rate of change of velocity. So that's the concept of something not only moving, but speeding up. Or something that's already moving and slows down. That's acceleration. Then we applied those concepts of acceleration, velocity, and change of position or displacement using these four equations and solved problems involving these different variables, and we were able to use the method of the absent variable to solve any of these different equations and know which one to use. Well, we're moving on now to a fifth concept, and that fifth concept is force, and that's F in sign language. And the fifth concept, force, is discussed in Newton's first, second, and third laws of motion. Well, what are these laws? Well, there are two concepts within the first law. The first one is inertia. They all have to do with force, though. And when we talk about Newton's first law, we look at one more concept, which is equilibrium. And inertia is the concept that things resist motion, they resist acceleration, unless you have a sufficient force to move them, then they will not move, and they will move in proportion to the force and in inverse proportion to their inertia. So, but what is inertia? Well, it's actually, there's another word that we use for it that's more familiar. Mass is the measure of inertia. So if you have a rock this size versus a boulder, this one has less inertia or less mass. Mass measures inertia. And if you had a rock this big, of course it would have a lot more inertia than this volleyball. I can apply a relatively small force to this and make it move. But if I had something, well, I don't have a rock, but I do have a bowling ball, and I can hit this and it doesn't move, it doesn't accelerate because it has so much more inertia. It only moves a little bit for the same force. So force is what makes things move. It's the why behind motion. And when you have a mass, you have inertia. And every single thing in the universe, every physical object obviously has mass, so everything has some degree of inertia or other. The idea of inertia then is measured by mass, and it means resistance to change of motion, of rate of motion or acceleration. It's really the idea of resistance to acceleration. Now, equilibrium has the concept that if we have balanced forces, if all the forces working on an object are balanced in each direction, then, believe it or not, it won't accelerate. That's right, you can have forces on an object, and it may seem a little strange, but if you think about it, if you have two equal forces on an object in opposite directions, equal in magnitude, then it doesn't go anywhere. It does not accelerate in any direction, that is. And so, even though those forces are applied, and you would think, okay, you have a force on an object, it's going to accelerate. No, not so if they are balanced. That's the concept of equilibrium. So just to review now on forces, which, by the way, forces are what make things move. It takes a push or a pull to make a mass move. It takes a push or a pull to make a mass move. Either a push behind it or a pull in front of it. The gravitational pull on this rock, or the buoyancy pull upward by the lower density of the gas in that balloon. And that is what it takes to cause acceleration of an object. It takes a force, a push or a pull, to make a mass accelerate. We saw that in equilibrium, the forces in one direction or another are balanced, that is, they're equal and opposite. And then there's, in the second law, the idea of unbalanced forces. For instance, you might have, instead of balanced forces on this weight, you might have unbalanced, and so it might accelerate in that direction. I might cause an unbalanced force on this volleyball. And that unbalanced force causes an acceleration. That unbalanced force is also known as a net force, and it's written this way. This symbol just means the sum of the forces, for instance, in the x direction. Now, what we know is that the amount that an object will accelerate because of these unbalanced forces is in proportion to the force. So rewriting this, the acceleration is going to go up with the force, and it will be resisted by the mass or the inertia that the object has. So another way to think of this is that if you have an unbalanced force in a particular direction, the object will accelerate in the direction of the imbalance. It'll go faster and faster in proportion to the force and in inverse proportion to the mass. This is the famous statement that we often simply see as F equals ma, the more common way of expressing this. Now, the third law is the law of action and reaction pairs. Action-reaction pairs are the idea that with every action there's an equal and opposite reaction. So as I push on this marker, if I push on this marker, it pushes back on me. I'm standing on the floor and my body is putting force on the floor. The floor is putting a force on me. That's Newton's third law, and we will study action and reaction pairs. That's all for today. Thank you for joining me. And we know that Newton's law, we can use that Newton's law